So welcome to the angular momentum chapter of quantum mechanics. First, we will define angular momentum according to classically. Then classically we know what is angular momentum, and later we will define angular momentum quantum mechanically. Okay, and we will see the commutation relations between the angular momentum components. We will deal with the finite and infinitesimally small rotations. Finite, we know if we do the infinitesimal rotation continuously, we will end up with a finite rotation. And we have already did this example of commutation of angular momentum. Rotations about the same axis will commute. Okay, that is a simple idea. We are not changing the axis, same axis, but different angle of rotation, but the angles are in reverse order. So we represent that rotation by RZ operator, RZ, R for rotation, Z for the axis on which we are rotating. So RZ 30-degree rotation followed by RZ 60-degree. So first we rotate through 30-degree, then followed by 60-degree about the same axis. The result is same as first we rotate through 60-degree, then we rotate through 30-degree. Okay, so the result is same. So we say that these two operators commutes because the results are same. Does not matter which operation you do first. That doesn't matter. You can either do 30-60 or 60-30 rotation. Result is same. So we say that rotations about the same axis will commute. Now consider rotations about different axes. I think Aloysia did that drawing also, posted the picture of rotating a book. So consider different axes, X, Y, Z axis. Now consider rotations about two different axes. Okay, each through 90-degree. That is what Aloysia posted, I think. So first we rotate through about Z axis through 90-degree pi by 2. Then followed by rotations about X axis again through 90-degree. So you can see that the result is not same if you reverse the order of operation. That is, if you first rotate through x-axis, about x-axis through 90-degree, then followed by z-axis rotation through 90-degree. You can see that you will end up with two different outputs. You take a rectangular box or any book or anything, you mark x, y, z axis and perform these two rotations and reverse the order of rotations. You can see that the book will, or the rectangular matchbox will end up with different results. So we can conclude that the rotations about different axes do not commute. Axes, plural. Okay. Now, I have already discussed this topic. Consider a vector v, vxi plus vyj plus vzk in Cartesian coordinate system. How to rotate this vector? I asked once in your class, and I think somebody told the answer. How to rotate this vector? to rotate, you have to multiply this vector with a matrix. That is the method. What is that matrix? And before that, we know that this also I have discussed. We have two kinds of rotation. One is active rotation and another is passive rotation. Active rotation means the coordinate system is fixed and the vector rotates. Vector only rotated. Okay. And passive means the vector remains static and the coordinate is rotated. Okay. So that is known as passive rotation. So any problem can be treated in both ways. Either you can consider active rotation or you can consider passive rotation. Results are same. Okay. So we don't have to do both. For one problem, you adopt any one kind of rotation. Okay. So usually we do the active rotation, where the coordinate system is fixed and vector is rotating. So normally we deal with the active rotations. Passive rotation, some problems, some others prefer passive rotation. So that is also possible. Two kinds of rotations are possible. We know that when a vector is rotated, what happens actually is its components gets changed. The components we usually call as representatives. We discussed that in the first chapter, representatives. These coefficients or components, this Vx, Vy, Vz are known as the components or coefficients of the vector or the representatives of the vector. So when we rotate a vector, what happens is its magnitude does not change. Nothing happens to the magnitude. Okay, only direction gets changed. As a result, what happens? The representatives or the coefficients gets changed. Okay, so let the new representatives or new coefficients are, new components are Vx dash, Vy dash, and Vz dash, primed coordinates, primed coefficients. Okay, so this rotation can be performed by a matrix. We already discussed that earlier. That is matrix R. Okay, so you can write as a general case, you can write this one as Vx dash, Vy dash, Vz dash. These are the coefficients of transformed rotated vector. Okay, and Vx, Vy, Vz are the coefficients of initial vector before rotation. So if you multiply with a R, matrix R, you can do this rotation. You can perform the rotation by multiplication with a rotation matrix R. So what is the R? What is the exact form of R? That is the question. I think somebody answered that question. So the rotation of a vector in space can be performed by a matrix R, and R should be an orthogonal matrix. Orthogonality means this kind of rotation. So the condition is for R to be orthogonal is R transpose equal to 1 equal to R transpose R. That is the condition for orthogonality. This R should be an orthogonal matrix. Okay. One more condition is that the magnitude does not change. So before and after rotation, the magnitude of vector does not change. That means root of Vx square plus Vy square plus Vz square should be equal to root of square root of Vx dash square plus Vy dash square plus Vz dash square. These are simple trivial things everybody know. Now let the rotation is about the Z axis. Okay, rotation is about the z axis. Normally we consider z axis rotation for all normal purposes. So consider the active rotation about the z axis. Okay, so how we can visualize this rotation? The vector rotates, consider the vector is in the xy plane. Okay, so we are along the z axis. The vector is rotating in the xy plane. So in which direction? It should be in the counterclockwise direction. Okay, not clockwise, counterclockwise direction. Then we take the angle phi as positive. That is the convention. Okay, the vector is in the xy plane. Let the vector is in the xy plane, and it is rotating about the z axis. Okay, but when the rotation is in the counterclockwise direction, the angle phi is taken as positive conventionally. For example, one more explanation: if you place a screw along the z axis, the screw will rotate counterclockwise so that the screw will advance in the positive z direction. Okay, so that way you can visualize the rotation. So this is the R matrix, rotation matrix, which rotates the vector through an angle phi about the axis z. So RZ phi means the rotation operator or rotation matrix, which we wrote earlier, is nothing but cos phi minus sin phi, cos phi. Okay. Then 0, 0, 1, 0, 0, 1. The third component, Z component, is 1. Vector is rotating in the xy plane. So cos phi minus sin phi, cos phi. This one shows that rotation is in the Z direction. Third component. Z is the third one. Okay. Now, if you want rotation in the x plane, you replace here x. You can find the y rotation also, that we will discuss now. Before that, you can expand this cos theta using the formula cos x equal to 1 minus x square by 2 factorial plus etc. Also sin x you can expand using x minus x cube by 3 factorial plus etc. Now you neglect the higher powers and take up to square of the angle. Okay. Then cos x you can write it as 1 minus x square by 2, and sin x you can take it as x. When x is very small or infinitesimal, you can approximate cos theta and sin theta like this. Okay. So you consider the phi as a very small or infinitesimal angle epsilon. Okay. Then you can write, instead of, so we are writing R is for an infinitesimal angle epsilon, very small. Infinitesimal means very small, tends to 0. So R is at epsilon. So we are rotating through an angle epsilon, very small, about the z axis. You can write it this one as cos phi. You can write it as cos epsilon, so which is 1 minus epsilon square by 2. Then minus sin phi, that is minus epsilon, sin phi epsilon, cos phi 1 minus epsilon square by 2, and all other things are 0, 0, 1, 0, 0, 1. Okay. So we have what we have done? We have neglected the higher powers of epsilon, like epsilon cube, epsilon to the power of 4, etc. And we approximated up to second power of epsilon. And we wrote this matrix. Okay. Now, using the same matrix, now you can write the rotation matrix along the x-axis like this. See, simply by taking the cyclic permutation. What is cyclic permutation? X changes to y, y changes to z, z changes to x. So that is the rotation about x-axis. So you can write Rx of epsilon. Okay. Actually, you take this block and just shift to the one row and one column. Okay. So 1 minus epsilon square, epsilon 0 becomes, starting from here, 1 minus epsilon square by 2 epsilon 0. Like that. Okay. You push each row, each column to the right once and each row to the bottom once. Then it should cycle. Means third column should appear as the first column and the third row should appear as first row. So you can write Rx of epsilon like this, rotation matrix about the x-axis. Similarly, once more you do the same kind of permutation, you will get the Ry of epsilon as this one. Okay. Simply practice this until you are expert. Just to do cyclic. Just to push the row and column to the right and bottom by 1. Then you will get the next. And it should cycle. The third, last row and last column should come as first one. Okay. So you will get the Ry of Z. So we have three rotation operators, Rx, Ry, and Rz for an infinitesimal rotation. Now you just check whether these are commuting. You simply check Rx, Ry equal to Ry, Rx. Just to perform the commutation. Okay. Check the commutativity about different axes. That is our, we are going to do. These are all classical things, nothing related with the quantum mechanics. Okay. Check the commutativity of the about different axes. So first we perform a simple matrix multiplication. Everybody know how to multiply matrices. So we multiply Rx, Ry. Okay. Rx, Ry. You can see that you check this multiplication. Everybody know how to perform this. You write two matrix, multiply the result, it will be like this. 1 minus epsilon square by 2, 0, epsilon, then epsilon square. Here it will be minus epsilon plus epsilon cube by 2. This higher term we will again neglect. Here also it will be epsilon cube by 2, that we will neglect. Okay, here it will be 1 minus epsilon square by 2 whole square. When you take the square, we again neglect the fourth power of epsilon. Okay, so that you can write it as, see, this term is same. This is 0, this is epsilon square, this term is same. This term you write it as minus epsilon by neglecting the epsilon cube. Here also we are neglecting epsilon cube and write minus epsilon. So this is epsilon, and this one you write it as 1 minus epsilon square. Neglecting the, that is a square plus b square we are neglecting, and minus 2ab is epsilon square. 2 into epsilon square by 2, 2 cancels and you get minus epsilon square. Okay, I think this is clear. We are neglecting again the higher terms. which is greater than epsilon square. We retain up to epsilon square, neglecting always higher terms because these are very small quantities. Very small quantity, you take the square, cube, they again diminishes very fast. Okay, now you consider the reverse of this one. You multiply ry rx. Okay, so earlier we did rx ry. Now you do ry rx. You can see that a similar matrix, but elements are slightly displaced. First term is same, second term is different. It was here 0, now it is epsilon square. Here epsilon, epsilon, epsilon square, it is now 0. This term is same, this term is same. These all other terms are same. Only these two terms are gets interchanged. Epsilon square and 0, this is epsilon square 0, gets interchanged. So what is the result? What is the conclusion? These two matrices are slightly different because these two terms are different. Okay, all other terms are same, but these two terms are interchanged. So matrices are not same. That means they are not commuting. Rx, Ry not equal to Ry, Rx. Okay, but we do one more assumption. We are going to neglect the epsilon square. Okay, then see, let us what is the result? How we can neglect epsilon square? You again assume that the rotation is very small, very small. Okay, infinitesimally small. Then you can neglect epsilon square. Okay, so we are considering infinitesimal rotation by neglecting epsilon square term. These two matrices becomes, here you can neglect this 1, 0, epsilon you can retain. Okay, so 1, 0, epsilon. This is 0, 1 minus epsilon, epsilon, 1. Okay, so if you neglect epsilon square term, you can see that these epsilon square are neglecting and 0 comes there. So the matrices are, simply write the results. By neglecting the higher terms, you write the both matrices. You can see that both matrices are same. That means for infinitesimal rotation about a different axis, we earlier said that the finite rotations about the different axes do not commute. But you can see that if the rotation is very small, infinitesimally small, the rotations about the different axes commutes. Okay, only if you neglect the epsilon square and higher terms, not otherwise. You don't neglect epsilon square, it is not equal. So if you do a very fine rotation, very small rotation about different axes, they will commute. Not for finite rotation, but for infinitesimal rotation. Our final conclusion is, for an infinitesimal, really infinitesimal rotation about different axes will commute with each other. Okay, I think that is clear. Is the idea clear? Is the idea clear? Somebody respond.
Yes, sir. Clear and.
Okay. And suppose we are not neglected the epsilon square term, higher terms. Okay, then what happens is you find the difference. Suppose we are not neglected the higher terms, then Rx Ry minus Ry Rx is this one, minus epsilon square. All other terms are same, and then that becomes 0. Only these two terms remains. Okay, so this is not Okay. Now you put in the equation number 2, you put epsilon equal to epsilon square. Means the angle, you put a substitute angle epsilon equal to epsilon square. Then what happens? Then R is at epsilon square is becomes R is at epsilon square becomes, I will show you what is equation number 2. See, this was equation number 2. Okay. In this, you put epsilon equal to epsilon square. Okay. Then what happens? This epsilon becomes epsilon square minus epsilon square. This becomes epsilon square, and here becomes epsilon to the power of 4 by 2. So you neglect that. That becomes 1. 1 minus epsilon to the power of 4 by 2. So epsilon to the power of 4 you can neglect. So 1, 1, 1. All the diagonals 1. Here epsilon minus epsilon square and here epsilon square. That is the Z matrix. Okay. So if you put epsilon, substitute for epsilon equal to epsilon square, then R is at epsilon square equal to becomes like this. One diagonal elements are 1. These two diagonals, these two upper diagonals, cross upper diagonals becomes epsilon square and minus epsilon square. Okay. Now you can see that this is nothing but R is at therefore you subtract a unit matrix I from R is at. Subtract the unit matrix 1, 1, 1. So what happens? R is at epsilon square minus I. I is a unit matrix of order 3 by 3. Okay, 3 by 3 order. So these diagonal elements 1 all become 0, and you get minus epsilon square epsilon square. Okay. So you can write these. See, these two matrices. These two are same. This matrix and this matrix are same. So you can equate the difference Rx Ry minus Ry Rx as Rez epsilon square minus I. Okay, simple matching of two equations. Rx Ry Z. Here you have to take care that these are epsilon rotations. Okay, epsilon rotations Rx Ry minus Ry Rx equal to Z rotation Z epsilon square, not epsilon. Note that point. This is epsilon square minus I. Okay, I think that is clear. Now, if the epsilon equal to 0, what happens? That angle is 0. Then Rx 0, 0 angle rotation. Then Ry 0, then Rz 0, which is nothing but I, unit matrix. Unit matrix means it does nothing, no rotation. So 0 angle rotation. Okay. So we can write R any 0, X or Y or Z, you can write it as I. So instead of I, you can write R any axis 0 angle rotation. That is I. Means I does nothing. I cannot do rotation. Okay. So instead of I, you can write R any 0. Okay. So this instead of this I in the equation number 10, you can write Rx Ry minus Ry Rx all Z rotation equal to Rz Z square rotation minus I. Instead of I, you can write R any 0. Okay. So this is a very important commutation relation between different axes. This is a very useful formula. You can we will after some time we will derive the commutation relation between the components of angular momentum using this relation. Okay. Now this session is going to be closed. I will start a new session. Okay. I think the idea is clear.